All right. So what we're doing today is mostly going to be adding, it's a couple newer mechanisms for addition, but for the overall addition reactions aren't going to really change. It's still break a pi bond, add something to each side. Just is it anti or syn? Is it Markov-Nikov or anti-Markov-Nikov? And what are you adding to each side? Those are the wrinkles that we have to pay attention to. And then a quick correction. When we were talking about stereoselectivity of oxymercuration, we said that the first part was an anti-addition. When you add the mercury and the oxygen, they get added as an anti-addition, so that they're on opposite sides of the ring here. And then I said, and then we do an SN2 to get rid of the mercury. That's incorrect. It actually goes through a free radical mechanism instead, which means we actually lose the stereo specificity on the mercury carbon. So the mercury carbon winds up making both anti and syn relative to the oxygen. So the first step has this stereo specificity, which will wind up mattering when we have sterics in particular. So where do we put the oxygen winds up being specific. But the hydrogen that we wind up adding winds up on either sticking up or sticking down. Or it's both. You get both syn and anti-addition. So very small detail. Most of the time, it's not going to wind up mattering. However, there are a few cases, and since I said it wrong in class before, I wanted to make sure to get that correction in there.
Those sectional pieces should the products be in equal parts, or would it be?
It's gonna depend a little bit on sterics. But they're gonna be close to. Basically, if it goes through a free radical intermediate, then free radicals are pretty close to a carbocation. They're not quite as unstable as a carbocation, but in terms of their geometry, they mostly go cleaner, like a carbocation. And so that means that we got roughly equal probability of hitting it from top or bottom.
Within 10% something.
Yeah, unless there are some other sterics involved. If there's some other group that could be getting in the way, then that could influence it. Like if we had a methyl group sticking up right here, then we have those 1,3 diaxial interactions, right? And you could wind up with that getting in the way of making the product with the methyl is cis with the hydrogen. You could wind up with it going from the opposite side more often. So in cases like that where you can look at specific sterics, and then you might get some more extreme, but for the most part, assume close to 50-50. Yeah, that's okay. All right. Right, so let's do a practice with one that has some sterics. So this is what's called a bicyclic structure. This is a biologically important molecule. This is alpha pinene. It's what gives pine trees their smell. It's why some beers smell particularly piney, or some
Like the hops.
Yeah, from the hops, and other evergreens and other nightshade plants produce a significant amount of alpha pinene. And so this piece here is what makes it bicyclic, is that we have a ring structure, and then we have a ring across the ring. So it's kind of like two.
A part of the ring that goes down, part of the ring that goes up.
Right. So you can see we count these carbons 1, 2, 3, 4, 5, 6. It's a cyclohexene that has carbon 1, or I guess this would be carbon 3 and carbon 5 attached by another carbon, by a bridging carbon. Is the way we think of it. So the other way you can visualize this. Did we talk about bicyclics last quarter?
Yeah.
A little bit. Okay.
A little bit. They'll only get 3 to 5%. That's what
Right, well, because if we call this 1 and this 2, then that would make the bridge between 3 and 5. So we would have something, if we're drawing this out flat. We'd have something like 1, 2, 3. And then there's 2 methyls off of that. But basically, think about it as that hexagon with a bridge across those 2 parts. But the big main point here is that doesn't really matter for answering this question, because that's not actually the functional. That's gonna affect stereos like we just talked about.
Right.
But as far as what's gonna actually react, it's still just gonna be the pi bonds. It's still just an addition reaction like we've been seeing. So if this goes through the hydrobromination. We can expect that we're going to, hydrobromination is hydration. And it is. Anti-Markovnikov. And anti-addition, so your hydrogen and your oxygen are going to be pointed in opposite directions. Is that what we decided on that one?
I think so. Oh, I think we said
Sin addition, okay, so it'll be your oxygen and your hydrogen are pointed in the same direction.
Yeah. Oh, I think I put either or. I don't know.
Well, let's double check that. When I'm not sure. What,
This one definitely is.
Oh, it's in addition, never mind.
it is in addition, okay. Then I lost my,
It's all right.
there's my mouse. So sin addition, but we're gonna add that. Oxygen to the less substituted carbon. If we started by adding the boron to one side and then the oxygen to the other side. We really added the hydrogen. To one side and the boron attached to the other side, right? So the hydrogen is going to attach here first. And sterically speaking, are we going to expect the boron to be attached below the ring structure or above the ring structure? Raise that first.
Below happens.
Probably. Hello,
Just for aesthetics, right?
Yeah.
So if the boron wound up, or if that boron wound up approaching below. And it did that hydrogen, the hydride and the boron were a syn addition, right? And then we wind up doing another syn addition to replace this, or another syn reaction to replace the boron carbon bond with the boron oxygen bond, right? So it seemed where if we had to guess, we would expect this to be our major product. Probably with some of the enantiomer of the where it's flipped. It's gonna be less likely.
Well, this is the reaction that you have to like think about the enantiomer popping up as well.
Right. There's gonna be some amount of this. But it's gonna be a lot less likely. Right, just because of the sterics, because we've got this bicyclic structure with these 2 methyl groups on it. Taking up the space above the ring, the odds that the boron is gonna come in here and attach above the ring are pretty low. So we would expect something like 90-10 maybe 95-5. Gonna favor this one pretty strongly just based on sterics. But then again, splitting hairs on that, that's 1 point out of 4. If this is a reaction problem on a test, it's 4 points for this one. Getting both of these drawn would be 3 out of 4 points. And then picking which one's the major is the last point, or maybe even half a point, depending on how I'm grading that day. It changes a little bit year to year, depending on what we emphasize. But the main point, I know we spent a lot of time on the stereochemistry, but the main point is anti-Markovnikov hydration. and then syn addition. Hydroboration, and technically it's hydroboration. Hydroboration oxidation, no,
Deboration and then.
I don't call it-
Hydroboration oxidation.
It is oxidation, second step, yeah. So the first step is adding the hydrogen boron. And then we make boron.
Then the oxidation.
The oxidation is coming in, the oxygen coming in here, replacing boron carbon bond so that you get O and then the boron.
Yeah.
And then you follow that up with replacing that entirely, so you would actually get a negative charge on that.
And then it can just be like an acid base equilibrium.
And then it just does a proton transfer, yeah. Right, so the mechanisms are helpful sometimes for actually getting, for splitting the hairs.
Yeah.
You just went through it, memorized those couple wrinkles, is it Markov-Makov anti, is it hydration? Is it syn versus anti-addition? That's gonna get you most of the way there, but the mechanism gets you the last little bit, we're talking about the specifics. So what if this went through oxymercuration? We have similar concerns, right? It's kind of a similar mechanism in that we're gonna do, it's gonna be two steps. First, we start by adding the mercury first. And then we add the oxygen. And that one is an SN2 attack, right?
Yeah.
So if we're looking at this molecule as a 3D molecule. First step is the mercury has to come in and attach somewhere to this pi bond to make that three-sided ring. Would we expect it to be sticking up or down?
Probably down. Just
Down,
because
yeah.
there's, like so much stuff on that 3-5 interaction.
So we wind up with the mercury going down like this. And then your oxygen is gonna come in and attach to the more substituted carbon. From the opposite side. So we wind up with something that looked like. If the oxygen is up. We had a methyl down. We had the mercury acetate. Down as well.
Would this reaction not favor? The oxygen on the one carbon?
So this is Markov-Makov. So
Yeah.
Markov-Makov means the oxygen on the more substituted. So it's gonna go there, because it's tertiary. And then we go through that second step, the demercuration step, which again loses the stereospecificity, so we're gonna have the other hydrogen here, but it's gonna be. Up and down, a mixture of both. Possibly figuring. It's kind of as far away, it's not. Too far away, so it's gonna be favoring probably putting the new hydrogen down, but again, there's already another hydrogen attached there, so we wouldn't be able to tell the difference anyway. In this one, we might get some of the oxygen going the other way. If you look at that, let me go back to the clarification on the stereochemistry.
Stairs.
Wait, what are you saying that the OH group would go? Wait, no, not.
So I pulled this from Master Organic Chemistry because they go into the mechanisms in more detail. And when you read what they say about, I love that they put in like the fringe cases, because this. In cases of extreme steric hindrance. You can actually get the oxygen and the mercury to go through a syn addition. So it's stereoselective, not stereospecific. We're gonna get some of the oxygen. The mercury is pretty much 100% gonna come underneath because that's big and the mercury is big. However, because there's sterics here that are gonna get in the way of this oxygen coming in to attack from above, there's some amount of syn addition that's going to happen as well because we have that steric hindrance. we'd still expect the major product to be this. But it's gonna be depending on how bad the steric interactions are. That's gonna affect what the exact ratio is of this one versus the enantiomer. And I guess that would actually not be an enantiomer, that would be a diastereomer, because we're not flipping these stereo centers. But the opposite of where this carbon is switched, we're gonna get some measurable amount of it. Normally, it would be like 1 to 2% of the syn product. In this case, would be more because of the sterics, it might be up into close to 10%, who knows? Without exact numbers, it's hard to say, but I like mastering organic chemistry because they made that caveat. It's usually this, and here's the exception. Because this is an example that is kind of an exception, that amount of sterics. All right, so questions about oxymercuration, demercuration?
So most of the time, it's going to be. What? Yeah.
The first
The
step
first
would be
step is
anti,
the
and then you
yes.
lose that specificity with the demercuration step.
Okay, and then it just depends on sterics mostly.
Right.
Okay.
And so this is one of those cases where it mattered that it was anti, because that tells us we're gonna mostly get this, because that mercury, the mercury is always gonna add. From the direction it's got the least sterics. Or like within sigfix always, because it's just so much bigger than pretty much anything else we're looking at. Which means that the oxygen has to come from above, even though that's less favored sterically.
Okay, I just wanted to clarify that.
Yeah. We're dealing with a lot of really finicky semantics almost.
Lots of.
Variables, yeah, exactly. This is kind of why I like organic chemistry, is because. In Gen Chem, if we covered something like this, there'd be a lot of, here's your general rule.
Yeah.
Know that there's exceptions, but we're not gonna go into why. We don't have to do that anymore. The further you go into any field. The less you have to say, but we're gonna ignore the exceptions. The more you get to say, let's dig into why the exceptions are there. So we can really understand it, which is satisfying to me at least. Then again, I'm the sort of person that likes starting debates at breweries just for fun, so. If I didn't wind up talking about science for a living here, I probably would have wound up as a lawyer at some point, just because. I like arguing about things, so. And it turns out lawyers that have background in the sciences are actually highly desirable by a lot of companies, because being able to understand the science behind. Things when you're arguing a case, is really helpful. Yeah. My buddy from undergrad, the same one actually, who said everything in organic chemistry happens because of electronegativity. He was a chemistry major, but he was pre-law. He went to UCLA Law and out of law school started making boatloads of money working for pharmaceutical companies in San Diego. So yeah, there's a career path right there too. Do something to set yourself apart from the other lawyers. Everybody's history major if you're pre-law. Almost everybody, just like almost all pre-meds are bio majors.
Not chemistry.
Sets you apart that way. All right. This was our first edition reaction that we looked at, right? Hydrobromination. It was acid catalyzed, so we went through a carbocation intermediate, and then we had our nucleophile attach. This is kind of how we define where the Markov-Makov reaction comes from, or Markov-Makov rules come from, right? Is if we're going to make a stable carbocation, we're going to put a positive charge on the more substituted carbon, and then our nucleophile comes in and attaches there. Well, when Markov-Makov was doing this research, they also ran into an issue in Russia when they were working on this, because people trying to replicate this kept getting the anti-Markov-Makov product, and they couldn't figure out why for a long while. It was especially confusing because they didn't even have the the terminology, Markovnikov's rule didn't exist because it was in the process of being discovered. They eventually narrowed it down to that the hydrobromic acid was contaminated with peroxides, had just like trace amounts of peroxide in the bottle. And it turns out if you have a little bit of peroxide with your HBr, you actually don't go through this mechanism. It goes through a free radical mechanism, meaning that we're dealing with unpaired electrons, which we'll spend, there's a whole chapter that will go over radical mechanisms. But the radical HBr reactions, you actually wind up adding the bromine and the hydrogen in opposite orders. So kind of like how hydroboration was anti-Markovnikov because we added the hydride first and then we added the oxygen. With the radical HBr, we add the bromine first and then the hydrogen. And that allows it to give us the anti-Markovnikov product.
So this is, so that, talking about that top one, that's the acid catalyzed. Bottom, when you have a little bit of hydrogen.
When it'll just say HBr, comma, usually it'll just say ROR, because it can be any peroxide.
Any peroxide.
So HBr, and just in the presence of any peroxide, so it could be hydrogen peroxide, sometimes you just see it written like that.
Any sort of thing that raises the pK up just a little bit.
It's really more about that oxygen-oxygen single bond.
Okay.
Because when you have an oxygen-oxygen single bond, it absorbs light in the visible region really easily to split into
Oh, so
two radicals.
So it can turn into the radicals, okay.
And then those radicals are so unstable that whatever they run into, they just steal an electron from it. And so what happens is if this runs into, like I said, we'll talk about this in more detail when we spend a whole chapter on it. But basically one of this electron would basically come over here. And you would wind up stealing one electron from this bond to make an alcohol, but then that leaves one electron of that bond with the bromine, and so you make a bromine radical as a result. And another note about arrows, because we're always thinking about the arrows. Notice that these arrows, they're curved, they're double barbed, meaning that you drew both pieces of the arrow. These ones, you'll notice, these are single barbed arrows. Only one electron moving instead of two electrons moving.
And that's all one electron moving in this.
Exactly. So because this is a radical mechanism, we're dealing with one electron moving at a time. We're still trying to form bonds that have two electrons, but we're only moving one electron at a time, which means we're always going to be left with an odd number of electrons. Which means that these reactions will happen really quickly, and they're what are called autocatalytic or self-sustaining, basically. Once you start this reaction, it'll keep itself going until you run out of reactants. Because this first step of making the two peroxide radicals is the slow step. As soon as you shine light on it for a second to start this process, then it keeps itself going.
It's just taking all that energy and.
It just, yeah, it starts. You're right, it takes a little bit, it takes a couple of photons to do this a few times, and then each time this happens. Once you have a radical, that radical keeps reacting and making new radical. So every time a radical reacts, you're gonna make another radical, which just keeps going. This is actually what caused the hole in the ozone layer. There was a class of molecules that were used as refrigerants they thought were really, really great. They were really great as refrigerants, and they're not very dangerous to humans. They're really stable at the surface of the earth. The problem is that when they get exposed to UV light, they break up into free radicals. And since they were lighter than air, they floated up into the upper atmosphere when they escaped, where there's lots of UV light. And so what happened is they turned into free radicals, and then once you started that process, they kept chewing up all the ozone that was in that altitude. And it's slowing down now because what'll happen is there's so this is the most likely thing to have happen.
Right.
But there is a probability, a finite probability that these two molecules bump back into each other. And if you have two free radicals bump back into each other, then they form a bond and you actually eliminated two radicals. But it's all a numbers game, right? If you have a couple radicals and a whole bunch of stuff that's not a radical, the odds are that the radicals are gonna run into something else and keep this process going. Until you start running out of molecules that aren't radicals. And then they might, you increase the probability they run back into each other. So even though we outlawed Freon and CFCs back in the 80s, I wanna say. And actually it was probably the 70s in the US, and I think it was worldwide, it was probably late 80s before they finally got all the third world countries to get on board with that.
Get on board with that.
Well, it's a little bit like, hey, we know we just gave you this cool technology that works really well, and we know that we've been economically depressing you for the last couple centuries, but why don't you go ahead and give us that technology back? Because we realize it's not a good idea. Like, yeah, they were somewhat justified to screw you. No, we're gonna keep using this because we need it.
Yeah, that's what I have to.
You ruined the environment. We're just trying to catch up with you. And that actually is an ongoing debate with developing nations across the country. Like, they weren't responsible for most of the greenhouse gases that were emitted after the industrial revolution, right? And now it's the only thing they can use, because they don't have the resources to build or to switch to sustainable. So how hard are we going to be on sub-Saharan Africa that has been just destroyed by colonialism and capitalism? When it comes to, no, you have to be economically or ecologically friendly as well. Anyway, that's economics in developing nations is a whole different discussion.
Is it common just to have the arrows, the half arrows above the line? I've been drawing up a little bit.
It's just out of convenience. It doesn't matter whichever way is easier, wherever you have more space.
So it makes
Yeah.
sense.
Yeah, exactly. And this is one of the few cases where we will actually draw arrows, electrons moving towards other electrons. Usually we try to draw the electrons moving towards nuclei when we're dealing with a pair of electrons. However, when we're dealing with one electron moving towards another electron, that's actually how you make a covalent bond. So we do actually have the arrows drawn like
It's the
this.
radical moving towards. the
Towards another,
electron that
yeah.
It's kind of just gonna
Exactly.
meet in the middle.
And this is one of the few times where you will draw electrons moving towards other electrons.
So this is just like a two-step process, or could it be like a four-step process?
So
I guess one of it would be, have to be steps with this.
So there's actually a whole classification, the rules for radical mechanisms. We actually have 3 different types. There's either initiation steps, which is like this first step where we click this to make that. And then there's propagation steps. Propagation steps are like this one or this one, where you wind up with a net same amount of radicals on both sides. And then there's termination steps. And so the way that we draw them out and how many steps we actually show with these depends a little bit on what product we're making. And what the reaction actually is, but there's usually gonna be like those 3 categories. You have to show initiation, you have to show propagation, then you have to show the termination, which is usually just like, oh, what if this bromine radical ran into this other radical? And then you wind up making some other product. But that's kind of the end of these reactions. These reactions end once you get enough termination steps happen. Otherwise, they just go on indefinitely. The earliest polymers, the earliest plastics that were made are mostly, and we still make a lot of them because they're really effective, were free radical mechanisms. They work really well, really fast, and they're pretty much irreversible, so you make a really stable product. The problem is you can't then use that product to make anything else. Early plastics are really stable and really useful, but they're all pretty much impossible to recycle. You can't melt them down and reform them, because once they're formed into that shape, they're basically one giant molecule. Which means they just stay as that. You can chop them up, you can break them up physically, but you can't like redissolve them and recast them anymore. So thinking like the old Tupperwares from the 70s and 80s, they had that really specific texture of plastic to them, right? It was really nice plastic, it's somewhat flexible, but you drop them, they would like fragment, they'd shatter.
Yeah.
Like that type of plastic was made by these free radical mechanisms. So we don't use it as much anymore because it's basically one use and you're done.
I think Tupperware literally like went into bankruptcy because of that, because their products were so good and that they would last for so long that no one would just buy them anymore. I think
Well, that and they had the multi-level marketing
that too.
as their business model, and those are only sustainable for so long, right? There's a whole thing in the 60s and 70s Tupperware parties where people would just like the Lululemon part, not Lululemon, but there's other like clothing companies now where they come to my house and we'll have a party. You can try on clothes and buy some from me. All those or like supplements. There's supplements are huge for that stuff now. Tupperware was one of the original. It's not quite a pyramid scheme, but it's almost a pyramid scheme. It's legally not a pyramid scheme, but it's right there.
It is a good scheme.
There actually is there's a good documentary on I don't know if it's Prime or Netflix right now that talks about a couple of those multi-level marketing companies. There actually is a very, very specific definition that takes it from being a multi-level marketing model to being a pyramid scheme, and it has to do with like the amount of money that you make by selling the product, and is it proportional to the amount of money that you make by getting other people to sign up. If the bulk of the money making comes from getting other people to sign up, it's a pyramid scheme. But if you can make money selling the product, not just getting other people to sign up, then it's technically multi-level marketing, and that's legal to a point. But it's a really hazy line, and it's not always obvious to people signing up.
Yeah. That's neat.
All right, so net result of this one, a lot of tangents in there, but here's our net result. If we have HBr with the peroxide, either H2O2 or written like this, we still get hyperbromination, it's just anti-orthogonal. And I'm not going to test you on this mechanism yet, because we're, like I said, we have a whole chapter coming up, either right before midterm or right after midterm, where we will talk specifically about free radical reactions. Right, so all you need to know for now is this.
Would midterm be like more mechanisms, products type of thing, or?
I think it's gonna be, I think I do 2 pages of reactions and 2 mechanisms. In the mechanisms are 10 points each in each product. And the reactions are a total of 40 points. So 60 out of your 100 is gonna be reactions and mechanisms. And then there's 10 points of application questions or short answer, explain this sort of thing, 10 points of wild card, that kind of thing. But I'll have a practice test for you when we get closer to it. But yeah, we'll definitely emphasize the reactions more this quarter. Yeah, that's fair. All right, so another new reaction, new mechanism. This one's called hydrogenation. So not hydration, not hydrobromination. Hydrogenation is adding 2 hydrogens to a pi bond. Yes. You can get this reaction to happen without the catalyst. But basically you have to be at like 100 atmospheres of hydrogen to force it to happen. So however, you can do this really easily if you have a metal catalyst. And we'll see a lot of cases. There's a lot of the rare earth metals that are really, really good organic catalysts. That's what a catalytic converter is basically, it's just a whole bunch of platinum, palladium, and rhodium. When you put those 3 together, you wind up with what's called the trimetallic catalyst, and the trimetallic catalyst basically takes unburnt fuel. And allows it to finish burning, finish reacting, so you don't get any extra mileage out of that. But it means what comes out of the tailpipe of your car is not a bunch of soot. And so that's why catalytic converters was a huge change in, especially in Southern California, but in a lot of major cities where people drive a lot. Requiring catalytic converters was really expensive initially, but it made the air much more breathable. My parents went to college in near Pomona in Southern California. And there's a mountain called Mount Baldy it's like 5 miles away. Yeah, it's not that far away. You know where Claremont is?
Yeah,
It was right down there. They went to Claremont.
oh, okay.
There were days in the late 70s where you couldn't see the mountain 5 miles away because the smog was so bad. Like more
I mean,
days
it's
than
like-
not.
It's close to like the LA area, like San Bernardino.
Yeah.
Like it's really close.
And the wind patterns basically push similar to the way that Sacramento gets all the smog from the Bay Area. The Pomona area and Claremont area gets all the smog from the coastline because the prevailing winds are pushing from the ocean in. Yes, they had a lot of days where they couldn't even see the mountain, and now it's really clear, you know, like
I
LA is
looked at a
pretty
study
clean
and
now.
it said it was like a fourth of the pollution in California is like from China, not like some of the winds.
Yeah, we get a lot, the wind currents bring a lot of things and. China both having more people and fewer catalytic converters, although I think most of their cars over there now are catalytic converters.
They got electric.
And they have a lot of electric too, but because it's also concentrated in certain areas,
Yeah.
a lot of it winds up blowing over. In really predictable ways, we catch a lot of that because of the jet stream.
At that point, is it worth having GR, like exhaust recirculation?
No, because most of our,
Having both of them,
it would probably be more worth it without catalytic converter, to be honest, because the catalytic converter, you're not regaining any of that unburnt fuel. You're just making it so that it doesn't turn into a pollutant. If you didn't have a catalytic converter, you could do something where you took the unburnt fuel and filtered back into your fuel tank somehow, recirculate the fuel that way.
well, what Ford did with their diesel engines to minimize emissions, is just have from the exhaust manifolds just go straight back into the intake. Which is really bad for the engine, but it's good for the dryer engine.
Yeah, so it's,
And they had,
I mean, I'm not sure what about diesel, I think diesel engines work at a lower temperature,
higher pressure.
higher pressure, so maybe it might be that because of the difference in the engine structure, that catalytic converters are less effective. And so to further increase the meet emission standards, they had to do that instead of the catalytic converter, or maybe with, I don't know the specifics of the engineering there.
Well, they do it with the gasoline as well.
Do they?
That's just an example.
Oh, okay.
What Ford did was really where it went downhill.
The catalysts that we're gonna use in this class are predominantly gonna be similar catalysts. Every catalyzed reaction, metal surface catalyzed reaction is gonna have a slightly different. Catalyst with platinum is one of the more common ones. So for hydrogenation specifically, platinum works really well. The problem is platinum is really expensive. So in the, green chemistry is kind of trying to find alternatives to some of these really expensive heavy metals. To both decrease costs and because platinum mining is not particularly good for the environment either. But there's still nothing for hydrogenation that works better than platinum. The net result though is same as before. You break your pi bond, you add something each side. It's just both sides are hydrogen in this case. And this one we get specifically only sin. And we'll see this a lot with they call this heterogeneous catalysis, when you have a solid or and the solid is what's catalyzing a gas phase reaction. or a liquid phase reaction. So if you have two different phases, where your catalyst is in one phase and your reactant is in a different phase, we call that heterogeneous catalysis. It's a huge research area because there's a lot of different applications for it. And it really, it's less than ideal. There are some aspects of it that are really nice. One, the catalyst stays in place. So like for a catalytic converter, if you've ever cut open a catalytic converter, the inside is like a really, really dense spider web of these three different rare earth metals, because that maximizes the surface area. More surface area means more reaction. So it's not just about rate with these, it's not just about what your concentration of your reactant is, it's also about how much surface area you have where your reactant can come into contact with your catalyst. And the way that they work is it's usually a version of this where you wind up with one or both of your reactants. They call it adsorbing. It's not absorbing, it's not being incorporated into the platinum. It's basically sticking to the surface. You wind up with these bonds forming where the hydrogen, these two hydrogen atoms were attached to each other, but they wind up making covalent bonds with the platinum instead. And the pi bond of your reactant will do the same thing, because both carbon and hydrogen are more electronegative than metals. And so what will happen is if you have a lot of extra electrons, those extra electrons wind up forming bonds with the platinum, because then the carbon can become more stable. And so because you have this process where we're actually making we're actually physically attaching your reactant to the surface, only one side of that molecule can actually react, the part that's attached to the metal. And so that's what gives us the syn addition. It is that surface. In most surface catalyzed reactions have some similar mechanism. Specifics will be a little bit different, but if it has to adsorb to a surface to do an addition, it's probably going to be a syn addition. This is the most common one. This is one we teach. But again, it's a big enough field of research that I took an entire grad level class on surface chemistry. Because this heterogeneous catalysis it behaves so differently than homogeneous reactions where everything is in the same phase. And there's a whole different language and different units that get used. Langmuir's is actually a unit. Langmuir is actually one of the premier journals in surface science, in surface chemistry. But it's also the unit named after the guy who first founded all of this. And it has to do with how many molecules are adhered per square meter of surface area. So you wind up with weird units because it's not just molarity now. It's moles per square meter. Yeah. It is. It requires a little bit of shifting how you think about things, but so predicting the product for this is pretty easy though. You break your pi bonds. If you wind up with where you have to worry about cis versus trans products, just remember it's always going to have the two hydrogens are on the same side. So the two hydrogens wind up cis relative to each other.
So can you have mixtures of, like, for example, hydrogen bonding with like that methyl and that ethyl going up and down?
Say that again?
So like on the top there, it shows like the two different possibilities. Will you get that just in general like 50-50 or?
Yeah. So in this case, they're both cis, but because these two things are different from each other, you wind up with an R versus an S.
Yeah.
You wind up with two stereocenters. If both of these were methyls, if they were identical to each other, then it'd be a meso compound, and we'd only get one product, right? So we only wind up with two products here because it's an ethyl and a methyl. if they were symmetric, then we would just get a meso compound. And if it wasn't a ring structure, then it might not matter at all too. All right, let's take our break there. Let's come back at 11. And we'll add last couple reactions. The last couple reactions are the same mechanism with different nucleophiles like we've seen before. So it makes sense. We'll stop here and then we'll add halogenation when we come back at 11. this room for 3 minutes and I got 2 new meetings.
Oh.
It helps to be hard to find sometimes. To be fair, those meetings already existed, I just hadn't been officially invited to them yet, so, but I knew I was gonna like it. It's not actually a surprise, but. All right. How about we look at halogenation? So, we had hydrobromination, or hydrohalogenation is adding hydrogen to one side, halogen to the other side. Mostly HBr, but also HCl to some extent. Hydrogenation is hydrogen to each side. Halogenation is a halogen to each side. So there's another one that's somewhat symmetrical. We wind up breaking pi bond, we add the same thing to each side. We really only see it with fluorine and bromine. Fluorine explodes when you try to do this, it's too nasty. Fluorine gas in general. And if there's something like, oh, we could probably do that with fluorine because fluorine and bromine both work. Almost always fluorine's off the table just because it's too reactive and too nasty. In iodine, it'd be too slow. It's still could happen, but it's gonna be not at a measurable rate at normal temperatures. So we mostly see this with fluorine and bromine. And like I said, it's just break the pi bonds, add halogen to each side. Just like we've seen before. And this one in particular, we only get the anti. And this was not a most of the time, this is an every time. All right, so if it was hydrobromination, it has to catalyze hydrobromination, we start by breaking the pi bond, make a new hydrogen bond, we get a carbocation, right? Is that feasible? Is that plausible for this reaction? If only anti is observed? What is that intermediate going to look like as far as geometry goes? What's the geometry? Does the carbocation or what hybridization? sp2, which makes it trigonal planar, right? Which means this second bromine would then be able to attach from either side. Right, there might be some steric considerations, but we would expect to be able to get both anti and syn. So the fact that we only get anti tells us this can't be the right mechanism. Because if it was going through this mechanism,
It seems like a quarter of this piece has been left out. This should all happen at once, right?
even if this, so this would be if the next step was this.
Right.
Then we would still get adding bromine to each side of the pi bonds. But what would the geometry look like? So let's say we started with our pi bond here. Methyl back. Methyl forward on each side. This first step then would break the pi bonds and add a bromine here and give us a positive charge here, right? Carbocations are sp2, like you said, right? Which means that that unhybridized p orbital is symmetrical, 6 up and down, which means that our next step, our nucleophile attack, could attach here or here. That would mean that we would get a mixture of anti and syn. Because if it attacks this side of the orbital, you get syn. If it attacks that side, you get anti. We don't see that. We only get anti. If we only get the anti, this can't be right. Right, and so this I like going through the logic of here's the experimental result, and then here's a proposed mechanism. Does it fit? Because we never actually we can't prove these mechanisms. we can't prove that this is what happens, but what we can do is we can prove it's not what happens. So the mechanisms that we're talking about, they're the ones that make the most sense with how we understand the concepts that we can't rule out. Right, and in science, philosophy of science in general, in the 20th century, we actually refined the scientific method. A guy named Karl Popper. Karl Popper basically said that science does not verify things, or a scientific hypothesis should not be verifiable. It should be falsifiable. You should be able, when you structure your hypotheses, they should be structured in a way that when you test them, if they're false, you'll be able to know if they're false. So we don't prove things true, we eliminate what's false. And that's really the heart of the scientific method. It wasn't really formalized though until the mid 1900s. And really, you can actually get Karl Popper's philosophy of science book as a free PDF online. If you look around, I'm blanking on what the name of it is. But it's actually, if you're into philosophy at all, especially modern philosophy, he writes a lot of really good stuff. He also he kind of resolved what's called the paradox of tolerance. Has anybody heard of that before? The paradox of tolerance is that if you have a tolerant society that tolerates all ideas, and all people and all beliefs, eventually it will become dominated by intolerance. Because if you tolerate intolerance, eventually intolerance takes over. Right, which seems like a paradox, right? But you can't tolerate intolerance in a tolerant society. The one thing you cannot tolerate is intolerance, or your tolerant society gets taken over. Karl Popper was one of the ones who resolved that, because he said, well, society is a social contract, and tolerant society is people entering into a social contract to be tolerant of everybody else. And intolerant people are not included in that social contract. They're in violation of it.
Yeah.
So therefore they're not protected by it. Just interesting. You see that term paradox of tolerance thrown around a lot in online forums and stuff when people talk about politics and theology and things like that. But Karl Popper, that was his other big contribution. In addition to the doctrine of falsifiability, he also came up with good ways to think about the paradox of tolerance, which is fun. Again, if you're into that sort of thing, worth reading up on. Right, and here's the exact same thing that I just drew. Right, if it was going through a carbocation intermediate, we would get both sin and anti-addition. That's not what we see, so it can't be going through a carbocation intermediate. We would still expect that, even if it did, we'd expect the anti-addition to be favored because of sterics, but we still get some sin. We observe 0 of the sin addition. Right, so, and my OChem professor actually worked in the lab that we just talked about that. That actually proposed this mechanism that's currently thought of as being the best way to understand these hallucinations. Basically, you make a 3-sided ring, just like oxymercuration.
So what I was getting at, I was saying this should all happen at once.
Okay, there you go. I just didn't hear you.
Yeah, I didn't say it.
Yeah. So what we do is we make this 3-sided ring that they call a bromomium ion, or if it was chlorine, you get chloromium ion. But basically that means that your first bromine winds up taking up both sides. It still keeps it from being a full carbocation, which means it's more stable. But a 3-sided ring is still not going to last very long. It's not great, and which means it opens it up to a ring opening reaction. That ring opening reaction is the second bromine coming in and doing an SN2. So because it's going in for an SN2, it has to be from the opposite side. This is what gives us our anti-product only.
So from molecules perspective, it's a nuclear film attack, and then from the bromine's perspective, it's a lot. Better.
So this bromine is gonna act as a nucleophile as well as have a leaving group lead at the same time. And then we get a nucleophilic attack that looks, other than the three-sided ring aspect, it looks a lot like any other SN2 we've seen, right? So net result, we get the trans product here, plus the enantiomer. Because if we think about this, this first step, we drew it as the bromine, the three-sided ring with the bromine above the ring. But we could just as easily have had the three-sided ring pointed downward, right? So we will get both enantiomers here. The important thing is that they're both going to be trans. You're not going to get the diastereomer that looks like the cis. And so lots of new reactions today, but a lot of similarities in how they work. And again, the main thing to pay attention to is I'm breaking a pi, it's an addition, I'm breaking a pi bond. What do I add to each side? Is it Markov-Makov or anti? Is it syn or anti? We keep those straight, then everything kind of fits into a couple categories. Couple. I won't say it's simple.
I love how much you qualify everything you said, because you need to.
Right, exactly. We got to be precise with our language, right? Is there any reason why we couldn't replace this with a different nucleophile, just like oxymercuration? The oxymercuration, we replaced water with an alcohol. We made it.
Or you can even replace it with like an amine.
Or replace it with an amine. Yeah. The most common, this is common enough that we actually see this. It actually has its own name. We can make a halohydrin by basically doing this reaction in the presence of water. The first step is still make the bromonium ion. The second step, though, is that the water acts as a nucleophile instead of the bromide. So it's still going to be anti. It's still making that three-sided ring. We just have water attaching to the second carbon. And just like with oxymercuration, the water is going to attack the more substituted carbon. So it still follows Markov-Makov's rule.
This one does?
Yes, the oxygen, it's a little bit less obvious to see because we did add something besides hydrogen to both sides. But the second step goes to the more substituted carbon. So the nucleophile that attacks second goes to the more substituted carbon, which means it's still Markov-Makov. All right, so we do still have, excuse me. That three-sided ring, just the first step looks the same. Make the three-sided ring with the bromine. The oxygen, when it comes in and attaches, is going to attach to the more substituted carbon.
But if it was a bromine ion.
If it was bromine, we wouldn't be able to tell the difference.
Okay.
It still would go to the more substituted if there.
Okay, so it
if you
still
wind up-
follows.
It still follows that. It's just you can't tell because you added two identical atoms. But if there was some you could imagine a stereochemistry case where which one adds second winds up mattering for whatever reason. The one that adds second will still go to the more substituted part. That's again really fringe niche case, but still would be possible. So good question. Net result, we broke the pie bond, we added something to each side, just like all the rest of these. And this is a really. We don't deal with these that often, and a lot of times this is actually something that occurs as an impure. Because you wind up with some bromine mixed in with your, or some water mixed in with your bromine. We wind up with this as a secondary reaction happening. We can cause it to happen, and this group in general. This type of molecule is called a halohydrin. Sounds like a Captain America bad guy to me. That always sticks out to my head, so now you have to think about that too. Or Halo, the video game. Ooh, Captain America and Halo. Now we're talking. I can get behind. All right, so here's a summary slide. And also practice for all these new ones. Hydroboration, oxidation, hydrochlorination, hydrogenation, halohydrin formation, oxymercuration. Try drawing all those products. The red is the specific details we need to pay attention to, right? And I guess the other one that we added in here. Go over, do HBr, H2O2. The hydrobromination with the peroxide. Also, I'd like to point out how far we've come already in this quarter. It's only the end of week 2 this quarter, right? Think about somebody who's never taken any OChem, looking at this slide. Nothing about it makes any sort of sense. Bunch of gibberish. Correct, because there's no stereo here. So, since you bring that up, we'll start there. That's the simplest one, right? You just get methyl cyclopentane. Yeah, no worries, and we've gotten through the stuff that I wanted to get through before the quiz this weekend, so we can take our time with this.
I was talking to Cody just before class, and they said that he question. People remember the mechanisms more than just from reactors and how it's structured.
Yeah, when you're in the thick of it, it's good shorthand, but if I was presented with this when I hadn't prepped for the lecture already, then I would still work through, wait, okay, those, figuring out all of these specific, especially the red letters.
Yeah,
I would have to go through the mechanisms for a lot of these.
yeah, especially
So.
like the 3 cent rings and stuff, helps visualize.
Yeah. So the quiz is going to look a lot like this. Give you a molecule, then give you all the mechanisms or all of the reactions we've added, all the addition reactions so far. So it's going to be just like this. Even a couple extra because it has you go through a do an elimination, do an addition, follow it by an elimination. To get the Zaitsev product and then do a couple more additions. So it's just more, it's reaction practice, set up a lot like this. All right, so let's start with, we'll go in chronological order that we added them in. HCl means we're gonna add a hydrogen to one side, chloride to the other. It's Markovnikov, so we're gonna put the chloride on the more substituted carbon. It's anti and syn because we go through a carbocation intermediate, but it doesn't matter for this reaction. We wind up without any stereochemistry. So there's our problems.
I thought
Oh, yeah. That's I guess the other halogenation here, the bromination we just added is not on here either. Add that one too. If we do the oxymercuration, demercuration, it's Markovnikov, which means we're going to put our oxygen on the more substituted carbon. But again, we're not going to get a stereo center. So it doesn't really matter that it's a mixture of anti and syn for that second step. It's anti-Markovnikov syn addition. So our anti-Markovnikov means we're going to add our OH to the less substituted carbon. And whichever side we add, if we add our oxygen going into the board, we add our hydrogen going into the board as well. Which means our methyl will be coming out towards us. So we'll get the trans product where the methyl and the OH are trans relative to each other. Plus an enantiomer. So this one, we did make 2 stereo centers because it was anti-Markovnikov. adding bromine without any water. Break a pi bond, add bromine to both sides. Anti-addition, so your bromines will end up trans relative to each other. Right, so I'm gonna draw that one over here where I have more board space. We'll get this molecule, or one bromine's into the board, one bromine's out of the board, plus the enantiomer. The anti-Markovnikov hydrobromination is not stereospecific. Those radical mechanisms, because they go through radical intermediates that are planar, we're gonna wind up with equal amount of the cis and trans, or relatively close to the equal amount of cis and trans. So we wind up with a methyl plus, or with, yeah, plus the opposite. Not the enantiomer, because you're only flipping one of the stereocenters. Actually, you will wind up with all of the possible stereoisters. Bromine and the methyl are cis, has an enantiomer. And then bromine and the methyl trans has an enantiomer as well. So we'll actually wind up with 4 stereoisomers for this one. Because both of those steps, adding the hydrogen could happen to either side. And then after you add the hydrogen, adding the bromine could happen to either side. Up or down. So we wind up with a mixture of all of those stereoisomers, roughly equal amounts. And that right there is also one of the reasons, another reason why free radical mechanisms kind of fell out of favor. Especially with synthetic chemistry, but even with material science, just because they're non-specific. You get just a mess of every possible product when you do free radical reactions, because those radicals are so reactive. And they don't preserve any sort of stereochemistry. So if you're trying to make something really specific, you almost never want to use a free radical mechanism in a synthesis problem, with one exception. And that's when you're starting with an alkane with no functional groups. A free radical halogenation is it basically pulls a hydrogen off and replaces it with a bromine or a chlorine, which then gives you a functional group you can work with, do elimination reactions or substitutions, etc. So if you have no other option, you can do a free radical reaction to add a chlorine here or bromine here, and then that gives you access to all the rest of those reactions we've been adding. Other than that, though, we try to avoid using free radical mechanisms as much as possible. Last but not least, the halohydrin. We're gonna put the bromine on the less substituted carbon, the oxygen on the more substituted carbon. And they have to be well, they have to be trans relative to each other. So we'll wind up with this and the enantiomer. There are only 2 stereoisomers for that one, because the oxygen and the bromine have to be opposite from each other. a lot of material. This quarter, right? Seems like we're going at a lot faster pace as far as like the number of things we're adding. Hopefully they all individually seem like they're making sense, but I can understand feeling a little overwhelmed by. Getting this slide or this quiz this weekend. It's one thing when it's me with the whiteboard, right? Just remember you have all the details here. There's a good reaction summary. At the end of the climb textbook, the old textbook, the one we're not officially using, that we kind of keep referencing though. So it might be a good idea to see if you can find a copy of that. I wouldn't spend money on it. But if you could find somebody who has an old copy of it or a digital copy.
Yes.
I don't know anything about that, but it would be helpful to have. There's a good reaction summary at the end of the alkenes chapter. And the additions chapter that looks like this with the answers. It doesn't have these notes. But if you're looking for something that you can use as sort of a cheat sheet that has details on it. So that you can answer the quiz questions this week under study. That reaction summary, and actually it might be linked. I might have it as a PDF attached to this week. If not, I'll look and see if I can find that. Or get yourself a digital copy. Let me see if we go into. If the quiz is going to go into these next slides. Well. We have the time and I let you out 20 minutes early on Tuesday, so we should probably actually use the time today. So in addition to these bromine three-sided rings and these mercury three-sided rings, you can also make what are called epoxides, which I think we've referenced before. We talked about those a little bit last quarter, right? The epoxide is a three-sided ring where you've got oxygen as part of the three-sided ring. Because oxygen is so much smaller than mercury and bromine, they tend to not be very stable. They react pretty quickly. But they have a very similar mechanism when they do react usually. Almost always, once you make an epoxide, the first thing it does is an SN2. You wind up just like with the bromination. When your nucleophile comes in and anti-attaches. The mechanism of making an epoxide is you have to start with what's called a peroxy acid, which looks like a carboxylic acid with an extra oxygen in there. So a lot of times you'll see those written as, and it doesn't even really matter what the peroxy acid is. But a carboxylic acid is CO2H. So a peroxy acid is CO3H. And when you do that, you get this sort of weird five-sided ring rearrangement happening. Basically, you wind up kicking it off. The net result is your peroxy acid kicks an oxygen out. And turns an alkene into an epoxide. 4 arrows. So this is what's called an electrocyclic reaction, because you got these electrons are almost going and all in a loop. Right, so in general, these arrows are going counterclockwise, right? Your alkene bond moves over to the OH group. The OH, the peroxide electrons move over towards the carbonyl carbon, but then the carbonyl carbon has to bump a pair of electrons to make room for those electrons, and they wind up grabbing the hydrogen. So you wind up doing almost like a hydrogen handoff from one oxygen to the other oxygen. Right, and so this is what the transition state winds up looking like. This is just showing the these electrons in the middle of moving, right? Same net result is what we have here. And again, the net result of that is an epoxide. And once you make an epoxide, that opens the door to, this is sort of similar actually to the halohydrin formation. Where the first step was you make that three-sided ring with bromine and then oxygen comes in. Now we make a three-sided ring with the oxygen. This is actually a way we can do it, create a diol, a double alcohol. Because if we then use water as a nucleophile, like we've seen in the past. We can wind up adding an OH to both of those carbons. So this is also called a dihydroxylation. So dihydroxylation, a hydroxyl group is an OH group, it's another word for saying an alcohol. So dihydroxylation, the net result is we broke a pi bond and we put an OH on both sides instead of a hydration where we did an oxygen on one side and just a hydrogen on the other. A dihydroxylation adds an OH to each side. Also, we talked about Scrabble in this last year. Chemistry terms and chemical names are valid words in Scrabble. So dihydroxylation actually is, if you could manage to play that in Scrabble, you get a few points out of there. In fact, there is one word in particular that is sort of the most possible points in Scrabble. You can play oxyphenbutazone. If people set you up just right, and you have the right letters in your hand, you can play oxyphenbutazone. And if you do that all the way at the edge of the board, you can actually hit all three triple words at once. And it puts the Z on a triple letter, and it puts you score 1,700 points. Like it's one of those things that only works if you have both sides know that you're trying to do it. You have to be so lucky, but it happens. And you get like 1,700 points.
So you could draw hydroxylation without a TI, and I could put TI on it.
And be dihydroxylation. Exactly. Get that triple word, those extra two letters there. So. And that second step of taking the epoxide and then doing the ring opening reaction, usually it's acid catalyzed. But basically, you're just gonna do the same thing we did with the bromination. We protonate the oxygen first, so that it weakens the epoxide, because it makes the oxygen a better leaving group. And then we do a nucleophilic attack with a leaving group leaves at the same time. So the net result is a dihydroxylation. But only works to make the anti-addition, only works to make the trans diol. You just remember that diol just means two alcohols on the same molecule. In this case, they're adjacent to each other. Another fun fact, diol, the soap, D-I-A-L, is so named because it's a dialdehyde. All right, so if you want to, so here's the summary slide, the last two. If you want to do anti-dihydroxylation, start by making an epoxide, so here's our peroxy acid. Turns into an epoxide. And then acid catalyzed ring opening. Which is just gonna protonate here to make a better leaving group, and then water comes in, acts as a nucleophile. And does an SN2. Backside displacement. If you wanna do a syn dihydroxylation, you've gotta catalyze it. Remember I had mentioned that that a lot of the metal catalyzed reactions tend to go through a syn process. Syn dihydroxylation uses osmium tetraoxide. Or osmium 8 oxide. Instead of making an epoxide and then adding the second oxygen later, this just basically gives us a way to add both oxygens at the same time. It's not actually a heterogeneous catalysis in this case. Actually, because the osmium does not get regenerated. It's not actually catalysis, it's actually a reactant. So that osmium 8 oxide. Adds, and you wind up making this 5-sided ring where the osmium is part of a 5-sided ring. And then you just oxidize it. When you do that, you wind up making, you basically similar to the hydrochloration where you just are going to displace this and turn those two oxygens into OHs. Alright, so this mechanism is not as we're not going to go into this step in detail, just like with the oxymercuration. So the mechanism of this doesn't matter as much. The main thing is that you know that the end result is a syn dihydroxylation. So now we have a ton of tools in our toolbox to try and put functional groups where we want them, right? We can do a hydration, we can do a dihydroxylation, we can do a halohydrin formation. We have a ton of different ways to add oxygens and halogens and hydrogens wherever we want them.
The second step of the syn dihydroxylation.
We're not going to go into it in detail. Yeah. It's one of those ones where it may be, there's probably a decent hypothesis for it, but it's not in the textbooks because it's not as well supported yet. So we're just gonna know it's gonna go through something similar like the demercuration, where the net result is we wind up with some osmium floating around, maybe it's metal, and maybe as osmium 4 oxide instead of osmium 8 oxide.
Same deal with the
Same, yeah. It's there. It's possibly recoverable to be reused if we recovered it and treated it to go back to where we started, but it's not the important part of the reaction for this.
Possibly, yeah.
Possibly, yes. And so you can see how I have to pace myself on these because they all make sense individually. But when you start thinking about how many of them we just added, it can be a little overwhelming.
We had quite a few today.
We added quite a few today. They're all the mechanisms that we talked about should make sense relatively speaking, but for now, and we'll practice with the mechanisms next week. We'll practice writing them out longhand and do some maybe in the class assignment. We have a paper lab next week. No, what week is next week's week 3. We have a paper lab the week after that. But we'll have sort of a your quiz next week. Or in class we'll spend some time just working through mechanisms, practice drawing those arrows, electrons moving towards nuclei. Work your way through to the right stereochemistry, all those steps. And so at this point, with this much volume we just added, know the net result of them. Is it Markov-Makov or anti? Do I make my syn or an anti-product or addition? what am I adding to each side? That's what we wanna get a handle on right now. Because all the mechanisms look similar enough that the more we practice with them, the more they'll start making sense and you'll see patterns and similarities. Any questions? We'll cover this next week. Oxidative cleavage is basically when we start breaking up the carbon structure. Oxidative cleavage, if you put ozone, O3, with the pi bonds, you wind up chopping it in half and adding a carbonyl to each side. So now we're really cooking with gas. All right, we'll end there. Quiz this weekend is just practice with the reactions. And we'll talk about those. Any questions that you have that come up over the course of the quiz, ask them as always. And I'll see you next Tuesday.